Summer, people from other countries or other time zones.
Starting a new band, the Zippers. Probably. So every once in a while, at our house, if someone says a phrase that's kind of weird, we'll turn it into a band name. And one of the best ones was flying neon duct tape. That was actually said in a sentence at our house. Yeah. Then I thought that flying neon duct tape would be a good band. So, pretty good. Yeah. My son. Oh, this is like perfect. This is like perfect for a matrix class. So, it's an N. Sorry. So, my son liked this as a band name, and what's cool about it is it reads the same this way as it does this way. So lot 110, lot 110. And he just wrote, a few weeks ago, he wrote a program to search for names like this, where you could have a 4x4 or a 5x5, where it'd pull real words out and you could put them together. So, is Jacob Deco here yet? Is Jacob here? Okay, never mind. So, yeah. Well, let's get started. I'd like to start us off with a prayer. Thanks, Ben. Amen. Thank you, Ben. Yeah, speaking of midterm, it's going on right now. It ends Friday, 11:59 p.m. I forgot to emphasize last time, please don't talk about the exam once you've taken it. Don't talk about the exam until you get the scores back, okay? Every once in a while, we'll have students, especially in large classes, they'll get sick. That's less of a worry this time because you can actually take it online, but something happens, they end up in the hospital, they have to go out of town, whatever, and they have to take it late, okay? So keep them from getting extra support on the exam, please don't talk about it. It happened once when the weekend after the first day after the test was over, we still had a couple kids that hadn't taken the test. They go sit in class, and the two students next to them are talking about all of the things they wish they knew on the exam because they had taken it. So please don't. And don't talk about it. There was another time I was walking by the math lab. Two kids had taken the calculus exam. They were in my class. At least one of them was in my class. I was walking by. They're just outside the door there. Other kids are in the math lab, in this room, studying for the exam. And they're talking about what they wish they had known on the exam. And I'm like, stop talking about the exam. So be safe. Just don't talk about it. You can tell people how long it took you. But beyond that, don't share anything about the exam. Okay. 3.5b, read the definition. So you're going to read up to the definition of dimension. You may as well read the definition of dimension. It's only like 2 lines. Watch the video. I'll make that after class today. Sorry, these videos are kind of long. There's just a lot in these sections, so I apologize. And WebAssign 3.5b, so do the WebAssign. And then 3.5a, I'm making a change. So there is a proof on there. Number 9 is a proof. It says proof something is in R3. Change it to R2. The proof will be a lot easier. So, and I think you will still learn what you need to learn by doing it in R2. So, but then he suggested getting rid of the proof question, but then you don't learn what you need to learn. So, okay. Before we, so if you guys want to take a picture of this, I'm going to do a quick something that I should have done last week. We're going to talk about using matrices to create codes and break codes and decipher codes. But if you want to take a picture of this and so you can think about this while I'm doing that, you're free to. Okay, so matrices are a fairly legitimate way to encode and decode messages. Not doing this very well. And don't go over there.
The very top.
Okay, so here we have, up here in this yellow, this is a matrix. This is the matrix we worked with last time. It does have an inverse, and this was the inverse we found. I just had the Excel do it for me. See M inverse, matrix inverse, boom. Andrew's shaking his head like this. Is that because you're like, so easy? Yeah. And here I wrote down a code. Pick me up at 8 at home. Okay? And I wrote down my code down here. So I'm going to put each of these symbols into a number. So if the tilde is my space. So, and then all the letters, they go 1 to 26. And then I put the digits 0 to 9 after that. So I have 37 things in here. And I could change this code if you want. Does someone else have another code that you could put this in? Yes. A tilde, yes. Yep, pick me up here at, how come that doesn't, enable editing. At, so actually I made it so as I type in something different, it does put the number, it goes and it looks up and puts the number there. So at, I think this is how you spell it. I don't know how you, is it tilde or til with a T, til? We'll just end with 2 spaces at the end. Okay, so pick me up at tilde. I think it's maybe how you spell it. Okay, so you can take any line like this. If you have a way to convert every character to a number, then you can put that message into a matrix. So I put this into a 3 by something matrix. I could keep going and make the message longer if I wanted to. So how do you encode this? If you take any matrix, you probably want one with integers, so whole number values. And as long as it's invertible, you can decode it. So if you take this encoding matrix here and you multiply it by this message matrix, you get this thing. Okay? And that's what you would pass to your friend or whomever, is you'd pass that matrix. There is a cool, you can, if you do like mod 37 or something, whatever we have here, mod 36, if you do mod 36, you can actually translate it back into A, B, C, Ds and numbers, and you could pass that to your friend. But anyway. So what does your friend do to decode this message? multiply it by the inverse. So let's do that over here. So let's say equals, we'll do a matrix multiplication and pray that this works this time. We're going to multiply the decoding matrix. But I don't know how to. F2 pound. I think that's the code. It's just F pound. F2 F. FGH, so H4, comma. And then the encoded matrix is this. And we multiply it and see something didn't work. What is wrong with this? Okay, we're doing minus. Yeah, we did get the.
First number.
Unbelievable. Okay, I seriously don't know what's going on. Every time I bring it up in this computer, it doesn't work. Okay, well, if you did do the matrix multiplication with this times this, then you would get another matrix, and you line them up back in a row to just undo this, what we did at the beginning. Here we have PIC, we put the 1693, we put down 1693. 11013, we put down 11013. 5021, put it. Then you would just go put them back and line them up in a row. So yes. That's right. So you encode the matrix, and there's lots of nice things about this. Like notice here I have T and T, but when I encode it, those two T's end up with different numbers. So you can't just start matching up character for a number. You can't do that. So it's better than just a simple cipher. There are still problems with it. With the power of technology, this is not super secure anymore. It used to be really secure. This is the complex version of this. A more complex version of this is what the Germans used and what the Allied forces were able to break for World War II and greatly shorten the length of the war. So the Enigma machine, that's right. Okay, dang. I don't know what's wrong, but it worked in my office. I'll make a video and show you guys it actually works. Okay, take about 30 more seconds, look at this, and then we'll talk about them. Okay. What do you guys think of the first one? Are vectors in standard position in the first quadrant a subspace of R2? So any vectors that form where both entries are 0 or larger. So we can write any vector up here. We can draw it on that axis if we want. Is this a subspace? Okay, he said if you put a vector there and then you multiply it by a negative coefficient, then it would not be in that area anymore. So if I multiply this vector by a -1, where do I end up with? I end up down here. And now that vector is no longer in there. Is the 0 vector in here? Yep. So the subspace has to satisfy 3 things, right? We have to have the 0 vector has to be closed under addition and closed under scalar multiplication. Okay. Technically, you don't have to check for the zero vector because it's under scalar multiplication, but you do have to check that if you don't check for the zero, you have to make sure it's not empty. And so we just tell you guys, just check for the zero. So, so is the zero vector in this? In this plane as we defined it in this first quadrant? It is. If x is 0 and y is 0, that's still in our set. Is it closed under addition? If I take two vectors where both of the coordinates of the vectors are positive, do I add them together and get another one that's positive? Technically not negative. Yeah. So it's closed under addition. But is it closed under scalar multiplication? It's not. We can end up getting out of there by multiplying by negative values. So not a subspace. Can you pull up the vector again? Okay. Questions on that first one?
Couldn't I do a stipulation that says x is greater or equal to, sorry, c is greater than equal to?
Oh, so he said, what about adding the stipulation that c has to be greater than 0, greater than or equal to 0? Yeah, so then you could create something with some more stipulations that would satisfy these criteria. So we might not call it that's not the way we're defining a subspace of Rn for this class, but you could. Yeah, it does satisfy some more general something called a group. So yeah, or a ring. So yes, you could. Okay, someone else had raised their hand. Yes.
Does closed under subtraction fall under scalar multiplication?
Oh, good question. That question was, does closed under subtraction fall under scalar multiplication? It doesn't fall under scalar multiplication, but it does. But if you have both of these, both 2 and 3, then you do get closed under subtraction because you can take one vector plus a -1 of another vector, which is the same as u minus v. So if it's closed under multiplication, then I can take the opposite of one of these, so multiply by a -1. If it's closed under addition, now I can take any vector and add it towards the opposite, plus the opposite of that vector. So we don't, yeah, so subtraction, we don't need to separate that out as another criteria. We get it from the combination of these. In fact, these are all linear combinations. All linear combinations there. We get with just those two things. Okay. Which of the following sets of numbers are closed under addition, subtraction, multiplication, division, and powers? So whole numbers, are they closed under addition? If you take two whole numbers and add them, do you get another whole number? Yeah, if you take any two whole numbers in that set, you add them together, you do get another whole number. So they are closed under addition. Are they closed under subtraction? If I subtract one whole number from another whole number, do I end up with a whole number? You can get negative numbers, right? If I take 2 minus 3, then those are 2 and 3 are whole numbers. 2 minus 3, I do that subtraction, I get a -1, and that's not in the set.
So we're talking whole numbers or natural?
So these are whole numbers, like this. Just 0, 1, 2, 3. So integers, now integers, are they closed under subtraction? Yep, they're closed under addition and subtraction. Are they closed under multiplication? If you take two integers, so they can be positive or negative, you multiply them together, do you get another integer? You do. Are they closed under division? No, because if you take like 3 divided by 2, those are two integers, you end up with 3 halves. That's not in that set. So then you have to, then you get the rational numbers. If you build what do you have to do to the integers to get it closed under division? You get the rational numbers. So, oh, it is closed under addition. Whole numbers are closed under addition. It's not closed under subtraction. So, yeah. So the integers are closed under subtraction. Both of these are closed under addition and subtraction. Sorry, addition and multiplication. But, This is more general, so just what it means to be closed under an operation is you can do an operation with the numbers in the set and you'll always get something else in that set. Like there's no way of getting out of that set by taking two numbers and doing that operation with it. But once we do subtraction with the whole numbers, we get numbers that aren't in that set. So, yes?
So wouldn't like every set be open under a division because you can always divide by 0 and that messes things up?
Well, it's not defined. So I failed to put under here that Q can't be 0. So with the rational numbers, you can't be divided by 0. Sorry. Yes?
Are whole numbers closed with powers?
Are whole numbers closed with powers? It depends if you take powers, or are they just whole number powers? Or if you take, can you have square roots, which is a fractional power? So if you go with fractional powers, then no. Then the real numbers aren't even closed with fractional powers because you can't take the square root of a -1. So then you get complex, and the complex numbers are closed under basically everything. So any of the operations you've learned, you can do the complex numbers, always just stay inside the complex numbers. We don't have to build any more number systems past the complex numbers. For the operations that you guys know. Okay, so that was just to practice thinking about what it means to be closed. Okay. Okay. All right. So take a minute and see if you can go ahead, take a minute, work on these problems, or work with the neighbor. Okay. See what you can come up with these. So number 1, let K be the set of all vectors V of the form x, y, and z, where y equals x and z equals x cubed. So is that a subspace? And show that the set of vectors on the line y equals a -3x is a subspace. So work on those for a couple minutes.
You're a bit better. You're welcome. Linear algebra, not cubic.
I'm smiling under my mask. Here's a little hint if this helps you. All right. What does your gut tell you on this one? Andrew says he wants to say yes. What did you say?
No.
Sam? You said no?
Yes.
Why do you say no?
I don't know, because I don't like cubes.
He doesn't like cubes. He wants to say no.
I want to say yes because they're all X's.
I want to say X because they're all X's. Okay? So if we're trying to show that they are, if we think that it's not a subspace, we just have to find one example where it isn't. To show, find two vectors that if we add, we don't get a vector of the same form. Okay? That's what? You said it's really easy?
No, you can't.
Then why did you say yes? Why did you say you thought it was?
My initial feeling.
Oh, that was your initial feeling. So did you write down examples? What did you write down?
So I'm collecting one for X and two for X. Yeah, those two vectors together, it's not.
Okay, so if you pick X equals 1, you get this one. This is it. This is in this set, right? It's of this form. 1 like X, and X cubed. Okay. And then if you let X equals 2, and 2, what would this have to be? 8. Okay. So what do we need to get over here if this is closed under addition? Well, you need to get something where we have a number, that same number, and that number cubed. Okay? So, and we get 3, 3, 9. Okay? Is that the same? I mean, is that of this form? No. So, this is, if we say, let S equal all vectors x, x, x cubed, where x is any real number. Okay, so this is a way to write down the set of all the vectors we're talking about. Then this is in S. This means an element of, or is in. This is an element of S. This is an element of S, but this is not an element of S. So that's enough. That's enough to prove that it isn't a subspace. We should have checked, is the 0 vector in this, in S? Yeah, at x equals 0, you do get 0, 0, 0. So that's okay. So if you wanted to do it in general, so then instead of picking 2 arbitrary ones, if you thought that it was, and like to prove that it was, you can't just pick one example. You might pick poorly, right? You might pick 0, 0, 0, and 1, 1, 1, and you get 1, 1, 1. You're like, yeah, it's closed under addition. Out of this one plus that one, I'm still in S. Yep, in that particular case, it is. You could have the 0 plus a 0, or the 0 plus that one, or the 0 plus anything in S. Yeah, but you chose poorly. So here and then there.
So in order to find that it's not a subspace, we have to find an example where it doesn't work.
Yeah, in order to show that it is not a subspace, you have to find a counterexample, like either an addition or a scalar multiplication, where you start with something of that form, or start with 2 things and add them and show that it's not of that form. Or start with something of that form, multiply it by a constant and show that it's not of that form. Or show that the 0 vector isn't in there. Yes? You can add the same point. We could have just added 1, 1, 1, 1, 1, 1. And you get 1, 1, you get 2, 2, 2. And that doesn't work. And that's the same as 2 times this vector. So you can do the same argument for scalar multiplication.
Isn't x equals 2 plus x equals 3 the better argument, because that 3, 3, 9 is for x equals 3 if you plug it in for that?
Oh, but this is squared, not cubed. So we need 3, 3, 27, right? So if you wanted to do general argument, I could pick x1, x1, x cubed, and x1 cubed, pick x2, x2, and x2 cubed. This These are any two points in S. I can add them together. x1 plus x2, x1 plus x2, x1 cubed plus x2 cubed. Is that the same as, what does this have to be equal to? So this number has to be the same as this, we're good. This number has to be one of those cubed. Are those the same? No, because x1 cubed plus x2 cubed is not the same as x1 plus x2 quantity cubed. So because of that, let's see, not equal, not equal. Okay? All right. Let's go back to, how about show that the set of vectors on the line y equals a negative 3x is a subspace. So I know a lot of you hadn't got to this yet, so I'm going to give you guys a couple minutes. How would you do this problem?
This is still working with B?
No, this is different. So the only criteria is you know that the relationship between the coordinates is the y coordinate is a negative 3 times the x coordinate. So you need a hint, you need a place to start. We could rewrite all of the vectors with this relationship as x and a negative 3x. So any xy coordinate would have to match this pattern. So what's your intuition here? Think it's linear, nonlinear? Sorry. You think it's a subspace? You think it's not a subspace? Subspace. Like this is a line through the origin. We already know that if we have one vector on here, that like this could be the span of one vector. Spans have. We'll get to the fact that a span of any set of vectors is a subspace. We don't know that yet. Isn't that weird that in math class you say something that you know, like I know, and then I say that you don't, like you guys don't know that yet? Like, isn't that kind of weird? It means like we haven't proven yet. You know, we haven't justified that that's true yet. So still, you don't hear that in English class, or you know, you guys don't know that yet. I just said that spans of any vectors are subspaces, but then I'm like, but we don't know that yet. That's just kind of a weird thing. Okay. So if we think, well, so does it have the zero vector? Yep, at x equals 0, y is 0, you get 0, 0, has the zero vector. So zero vector, check. Okay. Is it closed under addition? If you take two arbitrary points in here and add them together, is it also in here? Geometrically, it seems like they should. I can take any two vectors in here. If I add them together, I'm still going to end up on that line. How do you show that algebraically? We're going to use the same strategy that we did over here, where I'm going to have an x1 coordinate and x2 coordinate. So I can say x1, a negative 3x1, plus x2, a negative 3x2, equals x1 plus x2, a minus 3x1 plus a minus 3x2. And what does this have to equal? Oops. x1 plus x2. If I told you this was the input, this was the x coordinate, what would you tell me had to be the y coordinate?
-3.
A -3 times that. Right, whatever my x coordinate is, I have to multiply this by -3. So it better be x minus 3x1 plus x2. And then you can show that those are the same if you factor out the -3 here. You know, it's the same. Okay? So you could just not write that. You could factor that out and say this is of the form x minus 3x. So it's in the space, or it is in S, whatever we call that. So then we're good. So is it closed under addition? Check. How about closed under scalar multiplication? Closed under scalar multiplication. How would we do it? Can we just pick an example? Can we just pick one value and work with here? No, because we have to show it works for every single one. So, let's just pick an arbitrary one. So C times, and we just do x1 minus 3x1. Is that of the form x, and the y coordinate is a -3 times whatever that x is? Well, then you get cx1 a minus c times a minus 3x1. And that is cx1. If I factor out the -3, I get -3 times cx1. And so that's an element of S. It's of that same form. So we're good. Yep. So this is an example where you have to use the arbitrary ones to show that it does satisfy. Because you have to represent any possible vector. Here, we didn't have to do that because we were just proving it wrong. To prove it wrong in mathematics, you just have one counterexample. And here, we just found one counterexample. We didn't have to do that part. This was enough. Yes?
So if I took that equation, y equals -3x, and said +1, then it's all over, right?
Oh, so he said, what if we added 1 here to this equation? Why do you say it's all over? Why are we toast here? It's not going through the origin anymore. That's right. The other things might fail too, but so So then we'd have x, and then a minus 3x plus 1. So at x equals 0, I get 0, 1. And if I make this one 0, for this one to be 0, it has to be a third. And so there's no way I can get 0, 0. There's only one way for this coordinate to be 0. That's when x is 0. But then this is 0. There's only one way for this coordinate to be 0. That's when x is 1/3. But then that's 1/3. So, yes?
So if it is at the origin, you could plug in any value for x and see that it would work if you added them together.
Yes, like that's what we did right here. Right. Yeah. So a line through the origin is a subspace. A plane through the origin is a subspace. So, and any a three-dimensional subset of a large, well, even a three-dimension R3, which is the whole thing that contains the origin, you're good. But you could have three-dimensional space as a subset of R4 or R5 or R6. As long as it contains the origin, you're good. So I know, that's why we spend a lot of time in R2 and R3, because it's hard to imagine. Okay. Any questions on those? Yes. Sorry, say that again. Yes. Oh, yeah. So I didn't check that off. Yes. So if I take a scalar multiple, an arbitrary scalar multiple, which means the scalar is arbitrary and the point is arbitrary, I showed here that that's of the same form. So that's in S. Whatever the x coordinate, the y coordinate is a -3 times the x coordinate. So, yep. When would it fail? You mean multiply? So it actually doesn't work on this one. So you could do c times x1, x1, x1 cubed, c times x1, c times x1, c times x1 cubed. But is that the same as, if my first coordinate is x1, cx1, this has to be cx1. What does this have to be? It has to be cx1, the whole thing cubed, right? But these aren't the same here. We've got a problem because cx cubed 1 is not the same as c cubed x cubed for all c's. C is 0, you're good. C is 1, you're good. But any other c, well, -1, you're good. But those are the only 3. So it doesn't work for all c's. So, okay, yes?
So could we just safely assume it will always be a subspace if it's in 0, and it's not like a cube or a fraction?
I don't know if you should safely assume anything in mathematics. You should always be a little skeptical. Statistics too, you should always be a little skeptical. So if this is a linear combination, if this is a scalar multiple of this, you're good. That's actually what you're going to prove in number 9. So, but when you start adding things, you might be like, oh, I don't know. But if we added a -3x plus y, then we could actually write that out as 2 vectors, and then we'd span 2 vectors, and you'd be okay. Okay. Some of the things that you would have bumped into on WebAssign. So just in general, the idea of a subspace is really closely related to what we've been talking about as the span. If you think of all linear combinations of a set of vectors, we've been calling that a span. It makes a subspace. And so the subspace itself, kind of geometrically, is something we're already familiar with. Where it's going to be really helpful for us is when we talk about a basis. when we get something called the basis of a subspace. That's going to be really, really helpful to us to solve problems. Subspace might be like, this just seems like stuff I already know. And in a lot of ways it is. It's kind of repackaging some stuff we already know. Speaking of repackaging, oops. Nope, not peanut butter. I could have used a peanut butter example for this, actually. I should have. Okay. So if we call this A, this matrix A, what is the row of A? So this notation means the row space of A. And we can just write that down. That's 1, 1, 2, 2, 0, 1, and 0, 2, 3. But what I don't know is if I really need all three of those things. Yeah, I mean, yeah, some could be redundant. I might only need 1 or 2. So I could always say the row space is just the span. Oops, I meant span. I didn't mean just those. The span of all that. But I don't know if I actually need all those. That's where the idea of the basis is going to come in. The basis is going to be the smallest set we need to span the subspace. So we're going to do a slightly different problem now. Well, here, let me just quickly. So column of A is the span of the columns 1, 2, 0, 1, 0, 2, 2, 1, 3. So we have the span of the columns. I can write that down, but again, I'm not sure if I am dealing with more than I need here. In fact, this was the matrix we were working with last time. 2, 1, 3. This actually is a non-invertible matrix. The rows are a dependent set. The columns of the matrix are a dependent set. So I actually know, since we know it's not invertible from before, I know that I could drop one of these and I could drop one of these, and we'd still have the same span. What is the, okay, I don't think you've read about this. What is the null space of the matrix? So this wasn't in the reading, right? Yeah, so you guys will be reading about this next time. So the null space of the matrix, it's all of the vectors. It's all of the vectors x, or we could write it in x, y, and z, such that A times x equals 0. So they're all of the vectors that, so it's not all of the linearly dependent vectors. It's all of the vectors that we could multiply by this matrix and get 0. So the null space, we could always have at least one thing in the null space. 0, 0, 0. The 0 vector is always in there. If it's an invertible matrix, that's always the only thing there. But there are times when we care about this null space, and we want to be able to describe it. And so in your reading, you'll learn about how to actually calculate and represent it as a subspace. Hold on, back there and then here. The book will show that it's a subspace, like it'll prove that it's a subspace. So actually you have, if it's not just the 0 vector, then it is unique. Then you have infinitely many things. Because as soon as you get one in there that's not the 0 vector, you can have all the scalar multiples of that. So actually, I'll prove it on the video when we do it because it's on the slides. So So how would we do? And one of the big theorems that we're bumping up to is the dimension of these are the same. Okay, these have the same dimension. And the dimension of that is the rank. Right, the rank is the same as these. If you have an n by n matrix, then the dimension of your null space of the null, dimension of the null space of A plus the rank of A has to equal n. So little n, I should say little n. So any dimension that you lose in your rank, you end up putting it into the null space. So yeah, so yeah, it's exactly. Like every free variable you have adds a dimension to your null space. So we already know that every column vector that's not, I mean every column vector that's not a pivot column gets you a free variable, right? And every free variable adds a dimension to that null space. So yeah, it should look familiar. Is 2, 1, 2 in the row space of A? That's what I wanted to spend time talking about, and we're tough. So the book said, or WebAssign and the book say, hey, a nice way to do this is you augment it at the bottom. So 1, 1, 2, 2, 0, 1, 0, 2, 3, augment 2, 1, 2. You can do this. And then you try to zero it out with row operations, but it gives this restriction that you have to work top down. It's much easier to just transpose the whole thing and then do row operations for it. That's right. So, or you can transpose this whole thing, but that's the same as transposing this and transposing that and then putting it together. So it's much easier to do this. Then you don't have to worry about like the top-down restrictions. Okay, and the book does say you can do that.
But then you can't like swap the rows, can you?
So you still can. To find out if it's in here, this just has to be, this system just has to be consistent. If you're just asking, is this in the row space of A? Yeah, you can do any row operations, and as long as this is consistent, you're good. So in general, I would avoid this and just transpose your coefficient matrix, transpose this vector, and do it with the column ones. Then you don't have any restrictions on your row operations. Have a great day.